really appreciate. Thank you. I really appreciate the chance to talk here. I think this seminar has been really rewarding for me to participate in listening to it, and so I'm happy to give this talk. Um, Before I begin, I should mention that I'm going to talk about a few papers together and kind of the overarching themes in them, rather than focusing on specific technical results at some points. And as such, I should recognize all of my collaborators listed at the bottom of the slide here. I'll just point out both Riddiman, Bhattacharya, and Austin Brown are on the job market this year. So if you're still looking for somebody, you might think about it. All right, so what do I mean by reliable? I think that's the first question to answer. Reliable means that if we rerun the simulation, we're going to get a similar result within some kind of error that you've chosen. And so that's going to be the overarching theme of my talk. I'll spend a fair amount of time at the end thinking about what that means in the high dimensional large sample size setting later. So as an illustrative example to start thinking about what I mean by reliable, in this toy example, I simulated 1,000 IID simulations from a target distribution. What I'm plotting here is a non-parametric density estimate of the resulting distribution. And, in many cases, you don't want to just estimate a mean. You want to estimate something like potentially a credible region or other quantiles. And so what you see plotted here in the vertical black bar or black lines are the mean in the middle and then the 10th and 90th percentile. Now, the part that I'm going to talk about is the shaded regions. And so a fair amount of the first part of the talk is just going to be understanding what the shaded regions are doing and how to interpret them. So these are simultaneous credible or confidence intervals or simultaneous confidence region for all three parameters. And so you can see that they have a nice marginal interpretation, right? Because you can do them all simultaneously for a marginal. And they're not symmetric and they're all of different widths. And so it incorporates the level of confidence we have in each of those estimates. And so this is what we'll spend a little bit of time thinking about how this is constructed. So just as a general setup for the problem I'll be interested in, throughout capital F is going to be a target distribution that I'm interested in. We often want to estimate a mean or quantiles. And so forgetting about the notation, it's not too important except to notice that we want to estimate both means and quantiles simultaneously. And most often there's a vector of such quantities, and in any practically relevant application, you're going to want to probably a lot of these, one for each marginal distribution of interest if you're doing Bayesian analysis, for example. So we want to estimate a vector of means and quantiles. The standard stuff in the standard assumptions in Markov chain Monte Carlo, we want to simulate a realization of a Harris recurrent Markov chain with that right invariant distribution. And then, under moment conditions, of course, theta hat m will be the Monte Carlo estimate, just to be sample means and sample quantiles, the usual sorts of things. This estimate will converge with probability 1 to theta. And of course, this is what makes Monte Carlo work. This is really the justification for it. I want to note, however, just one piece of notation, M throughout will be Monte Carlo sample size, not N, which will be the observed data sample size, which we will also allow to be large later. Now, of course, after we don't simulate an infinite number, and so after some finite number, we have some unknown Monte Carlo error. And we want to assess that in some way. The typical way, right, the statisticians do this is through an approximate sampling distribution. And so if we normalize the Monte Carlo error appropriately, then we can have a central limit theorem. Where sigma now is, note it's a multivariate CLT, and sigma is a potentially complicated quantity because it accounts for both the temporal dependence and the dependence between components. right? So if we partition the covariance matrix in such a way that say sigma 1, 1 is just for the vector of means, right? And then sigma 2, 2 would be for the quantiles and the off diagonals or the cross correlated matrices. Sigma 1, 1 is complicated enough. You have the variance of whatever thing you're trying to estimate under the target distribution plus these infinite sum of covariances. Note that it's one matrix plus the transpose of another of the same matrix. In the reversible case, which is what we're concerned with today, because we're talking mainly about Metropolis-Hastings, these coincide and there's just a 2 out front. And of course, we need to estimate sigma in order to do inference about the Monte Carlo error. Well, I'll tell you conditions for the CLT later. But, this is, I think, something that anybody familiar with my work knows that I've spent a fair amount of my career on estimating this asymptotic covariance in sensible ways. And so here are 3 papers that, for example, we developed a method for initial sequence estimators, a method for, which are great. They're very stable, but they're computationally expensive compared to some of the other methods. And they're just generalizations of Charlie Geyer's original univariate initial sequence estimator from the early 90s. Spectral variance estimators are extraordinarily popular in the context of time series applications. In classical time series applications, however, they're not typically thinking about sample sizes of the same size, Monte Carlo sample sizes of the same size as you get in MCMC. And so while these things they work quite well in many ways, they're still a little bit more computationally intensive than something like the batch means methods, which essentially just break the simulation up into batches. And if they're large enough, they're approximately independent and approximately normally distributed, and it's easy to come up with an estimator for the covariance matrix that way. Under conditions, which I'm not really going to go into, any of these can be shown to have be a strongly consistent estimator of the true covariance matrix. And so as long as we can do this, and we can now with these methods, we should be able to make inference about our Monte Carlo error. I'll mention that there's been a lot of other recent work on extending some of these and generalizing. Dudukovats and James Flugel have a very nice other alternative estimator called the Lug-Sale, which is a generalization of spectral variance estimators that works really quite nice. So these are the ones I've worked on, but there's others out there and others that may be better in some settings. So how are we going to use this to construct reasonable simultaneous intervals? The natural thing to do is just to do the good old-fashioned walled type intervals, which in this case are displayed in this kind of just 2-dimensional setting as the ellipse, right? And so these are minimum volume. In many ways, they have many optimality properties. So the standard stuff from undergraduate multivariate analysis can be applied here. The problem with these from our point of view is especially in Bayesian analyses, we're often interested in making inference about marginals. And these do not have a convenient marginal interpretation. There are efforts to do that. There's a variety of types of ways of converting the ellipse to a marginal type interpretation. A very conservative method just projects the ellipse onto both axes. But that tends to be really conservative, especially if you're getting into higher than, say, 2 dimensions. So we wanted to create something that had a convenient marginal interpretation and would have the right coverage probability. We didn't really care if it was minimum volume in many ways, because in Monte Carlo, right, we control the sample size. And so we could just simulate longer to make the volume smaller. So one thing you could do for a convenient marginal interpretation is just ignore the dependence between components and do univariate intervals for each component. And so that's what you see displayed in the inner rectangle here. So the problem with that is going to be too small and it's not going to have the right coverage probability. Well, there's lots of conservative procedures for this. I mean, we can think about using Bonferroni, for example. And in this case, if you use Bonferroni in the setting, you might get something like the outer rectangle here. And so we have one that's too small and one that's too large, and that means there has to be something in between that does the right thing. And so this was our realization, is that if you look at the line segment in the upper right-hand corner, we can just keep kind of the ratio of the both sides, the similar, and just search along that line segment to find the right rectangular region in between. And so this can be done with a very simple bisection method to search along this line segment. And then you need a method for computing the normal probability in order to make sure you have the coverage right. And it turns out that we can use a very fast quasi-Monte Carlo algorithm to do that. That's actually just already implemented in R. We were thrilled to find somebody else had already done it. All right. So that's the basic idea behind doing these simultaneous assessments of error. So I thought I'd show you one example. We've implemented this in a software package. It's not on CRAN yet. It's on our GitHub page, but it's going to be on CRAN soon. All right. And so what this data is, so C-fades are variable stars. And so they get brighter or dimmer over time. This can happen either due to things passing in our line of sight of the stars or through some internal physical processes. What was realized almost 100 years ago, or maybe even a little bit more, is that there's a relationship between this period and its luminosity. And the reason why luminosity is important is because it allows astronomers to judge distance, right? And so on the vertical axis, you're seeing absolute magnitude, which, yes, it is negative, and the more negative, the brighter the star is. All right, it's just a convention in astronomy. It seems backwards to me, but it is what it is. And on the horizontal axis is the log 10, base 10 period. And so it's pretty clear there is a relationship, some sort of relationship between these. And so it's become essentially a homework problem now to fit a line to these methods. So what I'm going to do is for each so Y here is luminosity, absolute magnitude, and X is the period. And then we're just going to do a simple linear regression model. The priors are informative priors because people have studied this a lot, and I'm centering them around what people kind of accept as reasonable starting values, reasonable prior values to these. Now notice that it's simple linear regression, but I have two regression parameters. There should not be a comma right there. Beta naught plus beta 1, and beta 1, and the variance. So that means overall, I need 9 posterior features, a mean and 2 quantiles for each one. So this is so even in a very simple problem, you quickly get a fair number of features to estimate. So our package is called SimTools. And what you're looking at here is the output from running a Metropolis-Hastings algorithm on this posterior distribution. And you can see so the first column is the column for the intercept, the second is for the slope, and the third for the variance component. And you can see that we only ran it 1,000 steps. It looks like it's mixing great, right? The autocorrelation is very small. This is after a fair amount of tuning, to be fair, okay? And then at the bottom, you see the estimated each marginal posterior density, its mean, and its central 80% credible region. You can change those in the software package. And so you can see the shaded regions try to account for that width of these marginal confidence regions that we just introduced. And they're simultaneous across all 9 parameters, all 9 things you're trying to estimate. And so you might look at this and maybe you're happy with it and maybe you're not. If you want to decrease the Monte Carlo, for example, error in, say, the upper quantile for the variance component, we might run it, say, 25,000 steps, and it still looks like it works great. And now the Monte Carlo error, is so small you can't even display it on here. And so it's in this sense that I mean that the simulation will be reliable, right? If we reran this again, we would be likely to get something very close to these 9 posterior estimates. So I told you I would give you conditions for a CLT. So everything we're doing relies upon this theorem. The first 2 conditions are very standard conditions that you require even in the IID setting for quantiles, for a CLT for quantiles. Then there's a 2 plus delta moment condition, which is also standard in MCMC settings. Now, we did not assume reversibility in this, so you could do this under a weaker condition if it's reversible, like in Metropolis-Hastings algorithms. You could get rid of the delta, and just a second moment is required. We do require the Markov chain to be geometrically ergodic. I have not even told you what that is yet, but if you don't know, then it's essentially meaning that, at least in a qualitative sense, the convergence rate should be rapid. And then under these assumptions, for any initial distribution, there is a multivariate CLT for both means and quantiles here, and the batch means estimator is a consistent estimator of the asymptotic covariance matrix. We actually proved this theorem for strongly mixing processes, which include Markov chains, so it's more general than that. And we were actually, of course, you can weaken some of the moment conditions in the IID setting. So this result actually applies more generally than just Markov chains. So kind of a short, almost halftime summary here. Reliable simulation results can be based upon a multivariate CLT for means and quantiles. Estimating this variance of the asymptotic distribution requires kind of specialized methods, but can be done consistently. I actually think there's still room for more work in that space, especially in higher dimensional settings, where you might be interested in estimating a lot of parameters. In some of Wan Yang mentioned the neuroimaging work I've done in those settings. The posteriors are of dimension, let's say 5 million parameters. And you're not going to do this particular technique necessarily in that setting for all 5 million parameters. And so there is room for work in that setting, I think, for sure. And there's been some recent work on high dimensional sample CLTs that are quite interesting in that regard. We do have an R package that you're free to download from Dudica's GitHub page called SimTools. If anybody gets a chance to use it and you have feedback about how to make it better, we'd love to hear it. All right. And then reliable simulation results are going to require studying the convergence rate of the Markov chains. And so that's really going to be the rest of the talk. So, we don't do it just because we're interested in the convergence rate. We do it because we're interested in ultimately in doing reliable MCMC simulations. Okay. So in thinking about convergence rates, let's just look at and what affects convergence rates. Let's just look at a very simple one-dimensional example. Right, I'm going to assume that I have data and observations from a normal theta with known mean or known variance, and put a proper conjugate prior standard normal on the unknown mean. Right, it's an undergraduate homework problem to see that the posterior is this normal distribution. And it's pretty clear that the posterior distribution is going to change as n changes, as the number of observations change. Right, it's going to concentrate around the maximizer. So let's just use a random walk Metropolis-Hastings with a normal proposal having variance h in this context. So if we do that, so just to be clear, so we only have, it's all going to be one dimensional, and let's suppose we just have two observations, and our scaling is going to be h equal to 1. And so I simulated 1,000 steps of this. By the way, this Markov chain is easily shown to be geometrically ergodic. And so this looks pretty good. The trace plot looks pretty good. The autocorrelation function looks pretty good. There's some autocorrelation, but it's not bad in this context. And notice that up here, I'm reporting the empirical acceptance rate. So 365 out of the 1,000 were accepted. If all I do is change the number of observations to n equals 20, then you get something that behaves much worse. And this is probably not a surprise, because the posterior, as n gets larger, is getting more concentrated, but the Metropolis-Hastings proposal distribution, the scaling is not taking that into account. Well, and you see that now it's only an 8% acceptance rate. Well, if we change it to 200, then all of a sudden this is just an abject disaster of a simulation, right? 1% acceptance rate, you know, the autocorrelation is out of control. You'd have to run this thing for a very, very long time, you know, to produce anything reasonable out of it. So, but remember, this chain is geometrically ergodic. And so, you know, one thing we might ask is how can we fix this? Well, one way you can fix it is by changing the scaling to incorporate the number of observations, right? And so all I did here was, we still have 200 observations, and remember that was a terrible one on the previous slide. So all I did was, you know, multiply that n by 10, and there's a reason for that that'll come up later. And the scaling all of a sudden changes, and it looks great. You know, the 28% acceptance rate versus a 1% acceptance rate. So this is not something that's been studied. It has been studied in the mixing time literature to some degree, and I don't mean it hasn't been studied at all. But it hasn't, in my opinion, received the same attention that some of the say optimal scaling results, which allow the dimension to go to infinity rather than just, you know, so I guess my point is really that we need to pay attention to the sample size and the dimension when we're choosing the scaling in practical settings. So to avoid guaranteed failure of Metropolis-Hastings, the proposal scaling needs to account for both the sample size and the dimension of the problem. It's a little unclear. There's a little bit of work about this in the literature, but not a lot about what role does posterior concentration play in the convergence of Metropolis-Hastings algorithms. Can we identify when a geometrically ergodic Markov or Metropolis-Hastings chain is going to behave poorly? And can we identify generally when it's going to fail before we even implement it, because then we can avoid it? And so these are the types of questions I want to focus on a little bit for the rest of the talk. There's been a fair amount of work on, you know, kind of classically, when I was a student, it was all about total variation norm or weighted total variation norms. In the last 10 years or so, there's been a fair amount of work on studying Wasserstein distances and convergence in that context. So so I'm going to do both. I'm going to give some results for both. So in this case, the total variation norm is just the standard definition of total variation norm. And notice that it really controls the bias of bounded functions. That's where what it really focuses on. On the other hand, Wasserstein distances. So in this case, gamma is a coupling of the two distributions, mu and nu, meaning it's a joint distribution which has mu and nu as its marginals. And C in this case, in the integral, is just a cost function or a metric in our case that you have to specify. And so if we want to think about convergence in Wasserstein, then we want to look at the Wasserstein distance for a variety of cost functions in terms of the Markov kernel after t steps and the target distribution. Now, one reason why folks have advocated for thinking about Wasserstein distances is it controls the bias of Lipschitz functions. And so there's been some work in thinking about how it might result in improved scaling in higher dimensions. So it's going to turn out that in the work I'm going to do, the results are going to be slightly different, but qualitatively the same in no matter which of the metrics we use. And so that was one take-home message from what we've been thinking about. So I have to thank Guanyang for the inspiration for this result. Okay, in reading one of his papers, I realized that it could be extended past where it had been. So I want to give proper credit there. So the first thing we might do is think about a lower bound on the convergence rate. So if we define a sub h of x, so remember this is from Metropolis-Hastings algorithms. So the ratio here is just the standard Hastings ratio, and we have the standard Metropolis-Hastings acceptance probability. Remember, F is our target distribution. Q sub H is some proposal distribution that depends on some scaling H. So this is just at a point X, what is the acceptance probability? So it turns out that it's really pretty straightforward to show that this is you can construct a lower bound in terms of this acceptance probability in total variation as 1 minus a sub h. Now should not be very surprising to us, right? Because 1 minus a sub h is just the rejection probability. And so if you're not moving, right, then you're not going to converge. And so at an intuitive level, this seems obvious, but we'll see that we can get some mileage out of this in terms of scaling and behavior in higher dimensions. It turns out that for the Wasserstein distance, it's a bit more complicated. We have expressions for C sub d f, but it's just a constant. It's not that important. And it's still the same rejection probability, 1 minus a sub h, but now it's not just to the number of iterations, you also have the dimension of the problem involved in the lower bound. And so you can see that the qualitative result is the same if a sub h is close to 0, so you're not accepting very often, then convergence is going to be slow. So a lot of what I'll talk about going forward is when is a sub h close to 0? Can we identify conditions on that and how to avoid it in a variety of settings? Now, in fairness, if we want to calculate the integral exactly, that's, outside of pretty simple settings, that's hard to do. On the other hand, we can bound it pretty straightforwardly, and it's very simple to estimate using standard Monte Carlo methods by, say, just simulating from Q and doing an average. Okay, so it's not hard to get a handle on these at all. Well, to give you just a very simple, I'll go through some toy examples and get to some more realistic ones in just a few minutes. Let's just consider the setting where you just have a Gaussian proposal, right? Mu sub x is just some function. It can be, it's going to be arbitrary in the rest of the argument for this example. And h is our scaling parameter, and c is some positive definite matrix. Of course, the identity is common, but in our results, c can be anything, so you can get manifold versions of all these algorithms. So if you choose the mean function to be a constant, this would be an independent sampler. If you choose it to be the current state, it's a random walk sampler. You can choose it to be, coincide with the Mala algorithm, and so on. This is a very common proposal for a lot of classical Metropolis-Hastings algorithms. So in this context, it's easy for an arbitrary target distribution to show that this acceptance probability is bounded above by this quantity on the right, which is just a normalizing constant for the proposal distribution times the target density function. So certainly the value of f at the current state is going to impact this, as is the determinant, but those are all kind of fixed. Notice that it's h to the d over 2 in the denominator. And so this means, right, if we choose h to be large, even something like 2, okay, and d is at all appreciable, the dimension of the problem is at all appreciable, it will drive this acceptance rate to 0, which is bad, right? So this tells us right away that h should be chosen to be small, specifically less than 1, especially in higher dimensions, in order to avoid failure, right, before we even start. This is something I encounter in my courses when I teach applied MCMC type courses. Students often want to choose h to be large because they think that's going to allow them to explore the space and have a chance to do it. This says you should never do that, right? It also indicates that, unless you choose this scaling carefully, it can produce poor dimension dependence, right? Metropolis-Hastings can exhibit poor dimension dependence. It also suggests choosing the scaling proportional to d to the minus delta. In this case, remember, in this case, there's no sample size going to infinity. It's just for large dimension. Well, what's interesting about that is that's essentially the same recommendation you get out of a lot of the optimal scaling literature for these algorithms. And notice that we've made absolutely no assumptions on the target distribution. And so you're not having to assume independent components or other technical conditions to get to that result. So what I think this does is it supports the conclusions that are in the optimal scaling literature from a theoretical point of view that says that doing something like this can really help us avoid failure even in high dimensions, for arbitrary target distributions. Another toy example that just shows how we can explain how Metropolis-Hastings can fail, even though I think we've probably all seen this in applications, is now suppose that our target distribution is also just a normal with mean 0, that's just for convenience, and some arbitrary covariance matrix sigma, which is not the covariance matrix from the asymptotic normal distribution I was talking about before. So, and we're going to consider our proposal distribution with an arbitrary mean function. And I'm going to, just to make the math simpler, the expression simpler, just going to choose the proposal scaling to be h times the identity. So it's pretty easy to show that if the lambdas are the eigenvalues of this covariance matrix of the target distribution, then the acceptance probability at the origin, which is the optimal value, it's the center of the target distribution, is bounded above by this quantity. So it's the eigenvalue divided by the scaling that you get to choose. And so what does this say? Well, it says if the minimum eigenvalue over the scaling is close to 0, then the acceptance probability is going to be close to 0. And so it suggests that we should choose h to be smaller than that minimum eigenvalue. Now that makes perfect sense from, I think, when you see applications of this stuff, right? If you have a target distribution that has a really thin, narrow kind of strip somewhere, you don't want a big proposal, variance, because you're going to not tend to accept very often in that region. And so this just kind of gives some motivation for that. So those were just two simple examples to illustrate how we can use this technology to kind of say sensible things that I think are backed up by a lot of empirical experience from a lot of people. In Metropolis-Hastings settings, we might be interested in, like I said, geometric ergodicity. to ensure a CLT occurs. And the type of geometric ergodicity I was talking about there was in total variation. So what I mean in this context is the distribution of the Markov chain after t steps, and the distance between that and the target distribution is bounded above by some function of the current state, a number rho to the tth power, and rho is between 0 and 1. So this is a formal definition of it. You can also think about Wasserstein geometric ergodicity, and it is constructed pretty similarly. It's just the Wasserstein distance between the two distributions. And now, let's just say that rho and gamma, there's no reason why they have to be the same a priori without some work. But you can show that they're related. So in Metropolis-Hastings settings, there's been a fair amount of work establishing the existence of total variation geometric ergodicity, meaning they've established the existence of rho and c. There's been almost no work on constraining the values of rho and c outside of some not toy settings, but very standard algorithms like the Metropolis-Hastings independent sampler and some things like this. So it turns out that we can use these lower bounds to provide a lower bound on rho. And so it doesn't matter whether it's total variation or Wasserstein distances here. If the Markov chain is geometrically ergodic, then I'm just going to focus on total variation just to keep the presentation simpler. Then this constant rho is bounded below by 1 minus the infimum of this acceptance probability. Notice that this gives us an immediate corollary that if this infimum is 0, then it's not geometrically ergodic. And that's true for either total variation or Wasserstein distances. And so, this gives us a way, if we can talk about when this acceptance probability, this infimum will be close to 0, it'll give us similar information as to what the previous couple of slides did without thinking about that, right? It'll help us explain when rho is going to be close to 1 and meaning the geometric ergodicity, that convergence, even though a Markov chain is geometric ergodic, the convergence will be very, very slow. So here's another toy example. This was originally considered by Jarner and Hansen in their paper on establishing geometric ergodicity of random walk Metropolis-Hastings algorithms in 2001, I think. It's just, G here is going to be a bivariate normal, and H is a bivariate normal. B is just a known part of the normalizing constant here. But what we want to do is we want to set the target to be just a uniform mixture of these two distributions. So it's not bimodal, but you do get really kind of funky contours on the distribution, on the resulting distribution. So using our result, if you have random walk Metropolis-Hastings with a Gaussian proposal, then Jarner and Hansen established that this Markov chain is geometrically ergodic. But our result says the convergence rate rho is bounded below by the 1 minus 1 over 2 times b to the h. And so this tells you exactly if you start choosing h to be large, then the ratio here is going to be close to 0, and the convergence rate will be close to 1, and it'll be slow. So in this context, it gives you an explicit result that explains how that can happen. Okay, I have a couple of more substantial, more realistic algorithms or examples that I'd like to go through, and to show you that we can actually apply this outside of just toy problems. So in this case, I'm going to consider just Bayesian logistic regression with Zellner's G-prior. So I've written the target distribution down here. S is the usual sigmoid function for logistic regression. On the right is the G-prior for the regression components. Remember that G is something you have to pick when you pick this prior. So the first result that we have is that if we let beta star be the point which maximizes this posterior, And we're going to allow both the dimension and the sample size to increase, but not too, the dimension can't increase too fast at this point. Then with probability 1 for all sufficiently large n, the acceptance probability satisfies this relationship here. Now, here, it's pretty clear there's kind of a complicated relationship between n and d, but notice that if it also involves the prior parameter g that you picked from the hyperparameter. But if you choose h poorly again to be large, not to depend upon n and d, this acceptance probability will go to 0 really quickly. So instead of kind of thinking about the formula, it might be helpful to look at a graph. So I'm going to show you on the vertical axis, the convergence rate lower bound. On the horizontal axis, we have the dimension and sample size increasing from a dimension of 2, sample size of 8, up to a dimension of 14, sample size of 56. All right. If we pick a fixed scaling, like h equal to 0.6, then we get this kind of blue solid curve here. And we can see that as soon as you hit dimension 6 and 24, and 24 observations, it's essentially not converging, right? The convergence rate lower bound is approximately 1. What was really surprising to us is if you look at the scaling that you would get out of the optimal scaling literature, which does not explicitly account for the sample size, then you get something that actually converges slower than using just h equal to 0.6, right? Right, it gets closer to 1 faster. On the other hand, if you pick h equal to 1 over d times n, which would moderate that trade-off in the inequality we developed, you get this dashed line at the bottom, and so you can see the convergence rate lower bound is relatively small. Now, this is not a guarantee that this thing converges quickly. It just means it's not guaranteed to fail, right? So you might still have to work on it. But this 1 over d to the n is something that we observed in several examples, but we don't have a general theory for it, and that's how I chose it in the earlier example that I mentioned. We can also consider logistic regression with a flat prior. In this case, so it's the standard setup. It turns out in this case, we actually have conditions for posterior concentration around the maximizer of the posterior. And again, the dimension can increase, but not too fast. It's n to some power here. In this case, if the proposal is any normal proposal, then we can show that the acceptance rate at the maximizer is bounded by a constant k. We know what k is, the expression's in the paper, but it's complicated. In this case, you have 1 over n times h, so h is the scaling here, so you still have this n and this d to the n. And so it's very clear that you're going to have to accommodate both the sample size and the dimension if you want to, in your scaling parameter, if you want to avoid failure. Again, another plot. Now, this case, I'm just going to allow the dimension to be fixed at 10, and we'll allow the sample size to increase from 100 to 400. So if you pick a fixed scaling, like h equal to 0.1, it goes to 1 very quickly. So this is going to fail pretty quickly by 200 observations, for sure. And then we just plotted a few different results for various values, proportional 1 over to n here. And so you can see that smaller step sizes result in a smaller lower bound, meaning that you have a better chance at good convergence properties. All right, so, I'm really talking in this last part about 2 different papers, one with Ritteman and one with Austin. And in the lower bounds paper, there's a lot more in there that I'm not going to talk about, but I want to give you a general sense of what's in there. We do give a comparison to conductance methods. We develop general lower bounds under the assumption of posterior concentration properties. one kind of technical interesting result is we established that the existence, there are conditions for this, but their existence of a spectral gap is equivalent to a geometric rate of convergence for many Wasserstein distances. This is a result that was known since the late 90s for total variation in a paper, famous paper by Jeff Rosenthal and Gareth Roberts, but it turns out it's true for Wasserstein as well. And we extend it to some component-wise Markov chains where you are updating full conditionals along the way. Now, in Austin's paper, it's mostly random scan, but we're about to submit a paper for kind of standard deterministic scan algorithms as well. We have some explicit constraints on random walk Metropolis-Hastings. In particular, Ritterman and I developed weaker conditions for geometric ergodicity of these algorithms compared to the Jarner and Hansen results, mostly by refining their results. Their work established the existence of drift and minorization conditions, but did not actually give explicit ones. We develop explicit drift and minorization conditions, which allow us also to appeal to a lot of the upper bounds literature on total variation convergence, for example. So you can get upper and lower bounds on the geometric rate of convergence using that. We give applications to a large class of Bayesian generalized linear models. And in that case, we develop alternative lower bounds on the geometric rate of convergence using L2 theory. That's it for me. I'll stop with the citations for their two papers, which are both going to appear in Bernoulli, hopefully very soon.
Thanks a lot, Galin, for the very nice talk. Let me first